Hello and welcome to another video covering the OCR GCSE computing course. Today we're looking at topic number 12, which is all about sound and how sound is represented by binary. Let's get straight into it. And before I start this, this slide, so there's two slides in this video, a lot of information admittedly, but this slide, you don't need to actually know. The specification doesn't mention you having to know all of what's on this slide. In fact, most of it is stuff I've added in because I think it's very useful to understand this topic. So I'll point out the stuff you really essentially need to know, but it's still useful nonetheless. So sound is made by a surface vibrating, which causes it to send compression waves through the surrounding air. So some of this may be some GCSE physics recap for you. So this is just how sound is actually made, and it's an important concept to grasp. So sound is essentially waves vibrating through the air, caused by an object moving around, and we hear sound through our ears clearly, and they're a type of mechanical wave, a transverse wave, if that's GCSE physics again, as they work through movement. And you may think if they're mechanical waves, computers can interpret them. They can't though, because sound waves are a type of analog data. They're smooth data that sort of overlaps, and computers can't do that. We need digital data that is very clear in its where it's set out. In fact, we need binary data, which is 0 and 1s. So two elements of sound waves that are important to understand are frequency and amplitude. So first, frequency. So frequency of a sound wave is simply its pitch, so how high it is, how low it is. And frequency is the cycles per second, and these are measured in hertz. We'll look at another thing that's measured in hertz in the next slide, which you do need to know about. And so here I've just generated in Audacity, which is a recording program, a sine wave. And a sine wave is a form of transverse wave. The point of a sine wave is it's smooth. So most sound waves won't actually look like this, so look a bit more like this, although this is, of course, quite stylized. So the frequency is the cycles per second, and a cycle is simply one wave. So from what we call the trough to another trough, and the peak to another peak, that's a cycle. And however many there are a second, that is the frequency. So if you ever mention, so for example, AC current, alternating current looks a lot like this. If you look at a oscilloscope, again, physics, a lot of this is physics, it will look hopefully like this, and you can measure it. It goes across your screen, and however many cycles per second is your frequency. So if we have a frequency that's greater, so this has got a greater frequency, because as you can see, there are more cycles in any given time. So what this means, it means it's got a higher pitch. These sounds here will be a lot higher than these sounds here, and it'll just be a weird whining noise because most sound doesn't actually look like this, but this will be higher pitched. It will have a higher, it'll be higher pitched because it's got a higher frequency. So another factor of waves you may need to know about is amplitude, and this is loudness. So this is simply the height of a wave. So if you have another wave here, another sine wave, you've got, the amplitude is simply from the middle upwards or downwards. And so here, for example, this has got a much smaller amplitude. As you can see, this wave has got a smaller peak, a smaller trough, and therefore it's going to be quieter because it's got a lesser amplitude. So I do think this is useful. I would perhaps see exam questions on this, potentially. They wouldn't expect you to know about this, but you may need to interpret it, which I think is useful just to know about, and it helps with what we're going to do on the next slide. So sorry, I said I was going to point out what you definitely need to know. You definitely need to know that sound cannot be used by computers directly, and needs to be changed to digital because it's analog in the first place. So if we look at how this is done, and it's done through something called sound sampling. And sampling is another way of saying how to digitize the sound. You may hear it like that. So here I've got our sine wave, our sound wave here. So I'm going to take you through the simple steps in how it is sampled. So what it takes a reading of the sound wave at a predetermined rate, and the sampling rate or the sampling intervals are how often it takes a sample. And the sample meaning a reading. So for example, if we were to use a sample rate of 2 Hz, so it's measured in Hertz, what that means is 2 samples would be taken per second. So if we look at that, what that means is here at the top it's not labelled, but this is the seconds of the wave. So 1 second, 2 seconds, 3 seconds. So if we had a sample rate of 2 Hz, which incidentally is a very, very small, is terribly small. That would, the sound quality on this would be absolutely atrocious. 2 Hz, it'd be, in fact I've got a table to show this. If we were just to do the first 4 samples, it would be at 0, at 0.5 seconds, at 1 second and 1.5 seconds. So it'll move along the sampling at these different increments and take the value of the amplitude and maybe some other values, but that's not really the point. It's a principle I want you to understand. So it'll move along the sound wave and take these values. So this is just what I've guessed at, sort of thing. So at 0 it's roughly 0.25, at 0.5 seconds it's roughly 0, at 1 second it's roughly 0.1, and at 1.5 seconds it's roughly 0.25. That's a reading that it will have. And the values for the amplitude that have been taken at these different intervals, so the values for the amplitude is then converted and stored as a binary value. You can't store 0.25 in a computer, it needs to be represented as a binary value. So the sampling interval, I would have called it the sampling rate, that's what I've been taught, but the sampling intervals is what the spec mentions. So and it's a bit confusing because a faster sampling rate means that the samples are taken at smaller intervals. So you want small intervals for better quality. Yeah, so what I'm trying to say here is a greater sample rate or a lower sample interval, so you can't really get them mixed up, result in a greater quality sound. So the more samples you have, they're going to be a better quality of sound because it's less average readings. But the file size is going to be larger because more data needs to be stored. Okay, so another factor it doesn't actually mention, but this is the most logical factor because it's similar to one we looked at earlier in the images video, the previous topic, which is about color depth. Another factor is the sampling depth. So if you know about color depth, this may be quite easy to understand. So the sampling depth are how many bits represent the sound values. So for example, if 4 bits were used to represent the sound will have a far lesser quality than if 8 bits were used, because 4 bits can represent 15 values compared to 255, which 8 bits can represent. So essentially, if we only had 4 bits, 4 bits were being used, we could only represent up to 15 values. So for example, if the amplitude value here was great, so if it was 18 perhaps, it would get cut off. There'd be a cut-off point. It wouldn't be able to be represented. So there'd be an upper and lower limit that is limited by the sampling depth. So if we had 8 bits and we had our 18 value here, it'd be represented because 255 values can be represented. So yeah, essentially a greater sampling depth means that the quality is better because there's not going to be as many cut-off points, but the file size will be bigger. So to wrap it up slightly, you may be given example. This is just again, if I was an examiner, this is the sort of question I'd put in. If we had 3 examples here and it asked you to list them in 1 to 3, with 1 being the greatest file size and 3 being the least great file size and file quality, this is the sort of thing I would do. So if we had 15 kilohertz as our sampling interval, our sampling rate, and 4 bits as our sampling depth, it would have the smallest file size out of these 3 options. As you can see here, we've got 55 kilohertz, which is bigger than this, and also the sampling depth is bigger. Therefore, the file size is definitely going to be greater, and this is actually slightly smaller than this. It's all about looking at them and comparing their sizes, and yeah, that's just an example of maybe in a question you might get. So same for the file quality. This is going to have the least good file quality because the intervals are quite big and not many bits are used to represent it. And this, as you can see, hopefully you'll see a pattern, this will have the greatest file quality, and this is sort of in between. 22 kilohertz and 8 bits is sort of in between, and it's a compromise. You go for either a large file size and good file quality, or vice versa. It's all about compromise. But that's it for today's video. Hopefully it was useful, and yeah, hopefully I'll see you in the next video, which is all about instructions.